everybody. So I will introduce you mostly thermochronology, which is a science of dating thermal events. I think most of you know it's becoming quite popular. So most of you already seen maps with a lot of ages. For example, if I take a map of this area, you will see a lot of ages for this mountain in front of ages between 40 and 70 million years. And here the mountain in the background would be 10 million years maximum. So it means that this mountain were exhumed during late Cretaceous, Paleogene, and this mountain during Miocene. So this is usually what people know about thermochronology. But what people don't know is we can also now, if it was a fast cooling, a slow cooling, how geothermal gradient affects that, and the kind of story we can get with some detrital thermochronology analysis. So why I'm presenting that today, when we got the position in Hong Kong with Ari Seksek, Alex was like, oh, Mari, I present you Ari. She's an expert in Asian collisional system and geochemist. And Ari, I present to Mari, who is expert in Andean orogeny and thermochronologist. Please do project together. So this is what happened. So with Ari, we exchanged a lot, and especially about thermochronology, and Ari knows there is few data here in Mongolia, so we built a big project of geochemistry and thermochronology here, and she told me you can introduce this method here because usually people, they know basic, but not too much deeper, so I'm going to come back on the basic and then going a bit further. So the first thing, the principle is thermochronology, as I told you, is as a science of dating some thermal events. So with thermochronology, if you use different methods, you can date when your grain pass these geotherms, and you can have a very complete story of recent cooling. The main goal is just to infer thermal history of minerals or rocks in general. And for that, we use radiometric dating, but you use a lot of different thermochronometers that you can see in these pictures. Most of people, they know well high temperature thermochronometers that we call geochronometers, because the one which is used most commonly is uranium lead and zircon. And you can see on these pictures that uranium lead give you information about closure temperature above 800 degrees, which correspond to crystallization ages. So the closure temperature definition is the temperature at which a system has cooled. By cooling, we mean that, when you have radiometric dating, you always have a relation between parent isotope and daughter isotope. So what we do with that is when your system has cooled, you have no longer diffusion of the parent or daughter out of the system. And the system is your crystal. And on this figure, you can see that we have a lot of different minerals we can use, and they have different closure temperature according to the mineral you use and the parent-daughter isotopes you are using. So it's very useful if you want to understand cooling history from crystallization age to mid-temperature to low temperature. When people are talking about thermochronology, most of the time they are talking about low temperature thermochronology, which are fission tracks, uranium, thorium, helium, and cosmogenic nuclides that I will not define today. I will mostly focus on fission tracks and helium, because it's also the one you will see the most everywhere in any publication. So the parent-daughter isotope for that, so when you speak about fission tracks, you use spontaneous fission of uraniums that produce fission tracks, and which is affected by annealing. I will come back on all these processes with some analogies that will make it clear. And then for helium, you're based on the alpha decay of uranium and thorium isotopes that produce helium that can diffuse out of the crystal. The last low temperature thermochronometers we are using are called the trap charge mostly. It's related to the dynamic equilibrium between the different rates of electronic charge trapping and the trappings that we stimulate thermally. It was first used a lot by archaeologists to know when, for example, objects were buried. So when is the last moment the object was affected by the heat, by the sun, etc. And then people know they found a different rates to also apply this to tectonics, but I will not explain this further today. I will focus on the two other. So I will start with the uranium decay because, we have several kinds of doing uranium decay. And so this will affect the crystal in a different way. So when you have uranium decay, when you have your crystal, when your crystal crystallizes, you have a certain content of parent inside. And so for all time, you have a decay. And after a certain time, you have only daughter. Like we know for carbon-14 is quite fast, but for zircon, as Alex said before, we have zircons that are old at more than 3 billion years, so it's really hard to have only daughters. So most of the time when we are dating rocks, we always have a number of parents and a number of daughters. And with the radioactive decay law, we are able to give an age. If we know how much parent we have initially and how much daughter we have at the moment we date, we know the timing of the closure temperature event. So for fission tracks, I told you we speak about spontaneous decay. Your uranium is not stable, but it wants to become more stable. So what it did is usually split. So in the spontaneous decay, we split in two other elements that are lighter. And when these elements split, they will create, there's a strong reaction. Radioactive decay is quite strong. So it will create a scar in your crystal because it will displace elements around. And so you will create a scar of 16 micron long, most of the time. It's sometimes 15, sometimes 17, most of the time it's 16 micron long. And so throughout time, what you have is like when you start, you have few fission tracks, and through time you have more and more and more fission tracks because the fission tracks is not directly the daughter, but it shows that something happened. Like it shows that uranium decay, and so you produce daughters. So it's a kind of indirect way to observe the amount of daughters in the crystal. And then for the helium, we talk about alpha decay. So your uranium, during uranium decay, you produce thorium. And when you create that, the uranium will eject what we call the alpha particle, and the alpha particle is basically just an helium element. And so again, in this crystal through time, you will accumulate more and more and more helium through time. And so now I will explain you how we can measure the number of parents and how we can measure the number of daughters in this crystal. For fission tracks, usually we polish apatites, and then we put them in a nitric acid for not a long time, it's just 20 seconds. So just 20 seconds in the acid, and you reveal all the tracks that you can count in the microscope. And this reveals how much daughter you have in your crystal, how much reaction you have. Now to know how much uranium we have two techniques. So the first one is called the external detector method. Is the cheaper we have, but is quite long and is very time consuming because you need someone counting on microscope nonstop. But it's quite powerful. Like, so you put a mica foil on top of your apatite on which you have no uranium. Then you center a radioactive center. So you bombard your apatite, and then because of that, you will create more uranium decay. That will create scar in your mica foil. So after that, again, we put the mica in fluorhydric acid for 40 minutes, and you will reveal tracks, and you see it's exactly the mirror. Like when you look at the microscope, you have the mirror of the other apatite. And so here, which information is giving you is how much uranium you still have in your apatite. And so with that, if you just calculate how much daughter you have and how much parents you still have, you know how much parent you have initially, and you know how much daughter you have today. So with that, it's very easy by the law of radioactive decay to get an age of cooling. Then I told you there's a new method. So the first one was the external detector. Now people are using ICP-MS, but it's still in development because, so this method, you still have to count the tracks in the mica to know the number of daughters. But to know how much uranium you still have inside, you use an ICP-MS. But right now, recent study shows that this is working well if you have high density fission tracks in your crystal. If you have few, here's still a lot. You know, in Patagonia, sometimes I have just 2 tracks in the apatite. So when you have a very few density, you have to do mapping. This is very time consuming, and this is very expensive because ICP-MS is quite cheap if you want to analyze some dots like that. But you want to do mapping of each one is very time consuming and very expensive. And the other point is also zonation. Like if you have zonation in that you date only here as not representative of your crystal, so you have to make several dots. So it's still in development, but getting better and better. But the very good point of ICP-MS is you can get the fission track age cooling, but also crystallization age, because you measure other elements that give you uranium, lead ages of the apatite. And you can also get geochemistry, like trace elements, etc., that give very important information about if the apatite was a metamorphic, or this kind of volcanism, or this kind of magmatism, etc. So it's very important. Now for helium. Helium is much more expensive, except when you have Chinese friends that make you 400 ages for free. So, but usually helium dating, similarly, what we do is we have to pick grain one by one after measuring. So for all people here who are doing microscope, I'm quite sure you're already experienced when you measure a grain, you try to pick it and this grain is jumping and you have to do it again. So it's very, very time consuming. So you have to put a grain in a basket big like that, you know, it's very small. So you have pliers and you try to play. So it takes hours to do it. But when you finally do it, you send to a machine where you do helium degassing. So you heat your apatite enough to be sure that all the helium is degassing, and then you measure how much helium you have inside. So again, you have how much daughter you have inside your apatite. And then to know how much uranium and thorium you have, you dissolve your apatite in a solution, and then you measure the solution in the ICQMS to know how much uranium and thorium you have inside. So calculation is a bit more complicated because you have uranium and thorium that have decay releasing helium, but it's quite routine now. Now the main change are on the analysis. They make some step heating, etc. So there's still a lot of experiment to make these techniques more powerful. But yeah, now we know how it works well. So then I told you what you see mostly is like people usually they use thermochronology to date an exhumation or a cooling event. But many people, they don't know that you can also know if the cooling was fast or if the cooling was slow, just using thermochronology. Same data we are using here, the fission tracks and the helium. So I will make some gustatory analogy to make it clear because I think it's a bit hard to understand. If you take chocolate at normal temperature here, if you put a mark in your chocolate and you wait enough time, the mark will disappear because the chocolate is a bit viscous, no? Like if you take some chocolate paste, etc. But if the chocolate is too hot, if you make a track inside the track will disappear instantly. But if your chocolate is hard, you will make a track and the track will not disappear at all. Fission tracks is working exactly the same. If it's too hot, you create the tracks and the tracks is instantly annealed. If it's hot, but not that much, this is what we're in the partial annealing zone. So you made a mark in your apatite and the apatite anneal very slowly through time. And if the system is very cold, you just do marks and then nothing happened to the fission tracks. So it's very easy based on that to know if you have slow cooling or fast cooling, because if you have fast cooling, you have no annealing because you don't let enough time for the fission tracks to be annealed. And so usually you have long track length, around 14 microns for the average. While when you have progressive cooling, the tracks are shorter. It's about 10 or 11 microns for most of the tracks. And you see it's much more dispersed than when you have fast cooling. And so for that, obviously, you know, we don't measure tracks that are a bit tilted because if not, we don't have the true length. Because when we measure apatite on microscope, it's from the top surface here. So if you measure these tracks, you will not have the true length. So we always try to identify horizontal track, which is hard because, you know, to get this kind of tracks, you need to have a lot of tracks like here. Like here, you have a nice horizontal track. So that's why in many papers, you will not find this kind of element because it's very hard to find these tracks. So usually what you do if you want more tracks, because it's very important for you to know, to quantify the cooling, what people do is they put the apatite again in more acid, and they push the acid to go more inside by using existing tracks. And so that allows to observe more and more tracks inside. So people are doing sometimes, again, it's kind of expensive. So usually we try to, I mean, if we can measure the track, we do it. And if we can't, we just try to see if we can get a signal with other tracks. And so this is represented like that when we do modeling. So if you have a fast cooling, you go through the partial annealing zone in a very short time. And if you have progressive cooling, you are going in a longer time. And then you can have reheating. Keep that in mind because I will come back after to talk about the detrital thermochronology. Same gustatory analogy for helium now. I think I see you all drink tea here, but there's milk inside your tea. So I'm not sure you can see diffusion of tea or not. But if you take tea, if you take a cold water, imagine your bag of tea is your apatite and the tea inside is the helium. If you take cold water, you put the tea, no diffusion. If you take very hot water, it's diffused instantly. And if you put in between, the tea is diffusing a bit, but not that much. Exactly the same with helium. So at high temperatures, the helium is just diffusing, and that's why to measure helium, we just degas the apatite. I mean, we just heat the apatite to make degassing. That's very easy to do. And here we are in the partial retention zone because you retain the helium a bit, but still, mostly on the border, the helium is still going out of the apatite. And here you have no more diffusion, only the retention of the helium. And this is a matter of time, because if your tea is hot, but not that much, if you leave your tea bag for 30 seconds, you will have almost no diffusion. But if you leave it for 10 minutes, at the end, it will be like that. You will diffuse all the tea. So helium is doing exactly the same. So for fast cooling, you will have all the helium inside. You see, it's very high quantity of helium content inside the apatite. And when you have slow cooling, on the border, you have almost no helium because it's very easy for the helium to escape, especially by fission tracks. They use the fission track as conduct to go out. And in the core, you have less helium, but you still have, because it takes a lot of energy for helium to move from the core to the border. So you still have here helium in the core. And so how we identify slow cooling, because we are not doing this kind of mapping systematically, we look at the relation between the cooling age and the grain size. Because you imagine for a small grains, it's very easy for the helium to go from the core to the border. And so you will diffuse much more helium for small grains. Or if you have big grains, like most of the helium will remain in the apatite and mostly the border will be like that. So when you do a graph where you compare cooling age with grain size, if you see a relation going down like that, with helium content decreasing a lot with grain size, it means you have slow cooling. And if you see nothing, like if you have very fast exhumation and you see absolutely no relation, then you have a fast cooling. So that's why it's good to always take some grains of different size, just to look at this if we have something different. So for the apatite, I didn't tell you before, but the partial annealing zone is between 120 and 60 degrees. And for helium is between 140 degrees. The only problem with helium is, I told you helium can use fission track as conduct to go out. So through time, you do more and more fission tracks. And so you create more and more conduct for the helium to go out. And so same for zircon, you see the closer temperature can change through time. So if you have very old zircon or very old apatite, the closure temperature is changing. So we always have to take this in account when dating, because if you consider the partial retention zone and the partial annealing zone, you should always have older fission track ages than helium ages, because the helium ages show temperatures that are cooler. But the problem is in many cases, especially when you work in area where grains are very old, not very old, sometimes just Paleozoic rock, you can have these kind of things. Your helium ages can be older than your fission track ages. And this is not a problem, just a matter of that. So, and now we have the modeling software that take this in account. So for modeling, there's less and less an issue because now we are aware of that. So for modeling, we just input all this data. We input the helium analysis, the helium results, as well as the dimension of the helium, because we take care of the size of the grains. We put the track densities that give us idea of the dating. We took track lengths that give information about slow cooling or fast cooling. And you input everything in a software to model. And sometimes we put stratigraphic content. Like if you want to date Jurassic sedimentary rocks, you know that if it's sedimentary rocks, means during Jurassic, the rocks were on the surface or close to the surface. So what you do is you add a constraint here to say, okay, during Jurassic, my rocks were around here. And then with the data you input here, the model will look for the best way to create the perfect model and know if you have slow cooling or faster cooling, etc. So for modeling, I will explain you shortly, but it's mostly statistics. So we have two kinds of modeling. The first of modeling is a Monte Carlo analysis. So you just put all this data in your software. So you see here is the initial point. Here is the point we are today. So present day temperature. And here is all your data that you input, and here's some constraint. And you tell your software, okay, I have this, and I want you to find the best way to explain all this data, including the constraint, etc. a new model will find the best path. Then we have something a bit more complicated, as when you have, in statistics, what we call the Markov chain Monte Carlo, so MT, where you have a Bayesian and a stochastic approach. So that means after the software finds the best path, you will ask the software, can you please look around the best path? What if there is no better path, but just in this area? So you will force the software to explore all the paths here around. So the software knows, like, identifies that this is not a good way, this is not a good way, this is a good one. And now I'm asking you, can you explore around to see if we cannot find better just here around this best path? And so for that, we have two software that are very useful. So we have Helium-FT and Qt. Helium-FT is doing only MC analysis, so it's very good to have an idea of best path very easily. FT is user-friendly. Qt, you need to read the manual or to know someone who knows to explain you when you use first, because it's much more complicated. But Qt is running MC analysis, so at the end you have much more powerful results. So usually we use FT to just get an idea of what we have, and then we start exploring everything with Qt. The good thing with FT is there is no artifact. Like if you have only one data, which is bad, you see big uncertainty, FT will tell you, me, I cannot find a way. It's too hard to find a good way with this kind of data. Qt will find a way. So sometimes we will find a way, even if it's hard to know, there's not enough constraints. So you have to take care when you use Qt. But the very good thing is, like, Helium-FT is quite long to run, while Qt is running very fast and very deeper, because I told you it's exploring very disparate path around the main path. And so the other points is we have some limitation, which is very important with FT, is like in FT, you can input only cooling edge and track length, while Qt, you can also input chemistry parameter, because when you measure with laser ablation, you have a lot of parameters that you can also input in Qt. For most of people working, we don't have so much data, so having 10 input data in the modeling, it's okay. But in some cases, you have a lot of data for one sample. And so in that case, Qt is powerful because you can see you can input until 30 ages for one sample. So it's quite powerful here. And then we can also explore several samples at different elevation. So this is what we call vertical profile, and same, I will explain shortly what it is after. And so here is the kind of result we get. So when you see this green and purple colors is Helium-FT. So usually it's very basic models that run very fast, but for easy model it's perfect. Huh? If you don't have a lot of data, you don't need to go with Qt. Like Helium-FT is running perfectly. And so here you always have like the acceptable path in green and the very good fit in purple. If at the end of the model you have no purple path, it means that FT is not able to find good path, and so you can forget interpretation about that. It means it's too complicated. And for Qt, we like to use the likelihood model, because the likelihood show if the data are well reproduced or not. So every time you have pink, this reddish here, it means that all these paths, they reproduce well the data. And this black line is just an average of all the good paths. So you can have an idea. So you always consider this path here in black and the 95% intervals that take into account all the good data. And that gives you a good idea of cooling history of the rock, usually. So now why this is useful for tectonics, because there's a ton of applications for thermochronology. Some are used routinely now, some are still very complicated. So the first thing is, you all know that if we go deeper and deeper, because of the geothermal gradient, temperature will increase slowly. So if you know the fission tracks, apatite fission track closure temperature is 110 degrees. If I have a normal geothermal gradient, so 30 degrees by kilometer, how much, and considering the surface temperature is 20 degrees, how much kilometer represents this temperature, you think? How deep? Yeah, 3 kilometers. But if your geothermal gradient is 60, how much is this? 1.52 maximum. So most of people, what they do is they neglect the geothermal gradient when they do interpretation. Why it's very important, because I mean, if you want to date exhumation and you say, oh, apatite fission tracks is 120 degrees, I have an edge at 60, it means that at 60, my rock was at 3 kilometer depth. No, it means your rock was at the geotherm 110 degrees. And then you have to look at the data about geothermal gradient to know if it was 3 kilometer or less according to how high was the geothermal gradient in this area. So exhumation, I think, is something, some people, they have problem with the definition of exhumation, so that's why I'm just coming back slowly here, as the act of bringing up something to the surface. So like if you have an apatite which is at 110 degrees and want to reach the surface, want to be cooler, if you do only uplift, it will change nothing. If you do only uplift, your apatite will still be at 110 kilometers. So to do exhumation, you need denudation. So usually erosion is a big factor for that, because if you want to get your system cooler, you need to remove rock on top and to decrease the geotherm where the rock is. So it's very important. And this is something we saw easy. I talk about vertical profile. It's something we see easy in vertical profile. Like if you take one catchment, the rock on top will give older edges, thermochronal edges, not crystallization, thermochron edges than the rock at the bottom. Why? Because this sample passed the geotherm 100 degrees much before this rock. So it's completely normal to have a difference here. And same if you work on detrital. On detrital, you will have a lot of grain of different ages. All the grain with old edges are coming from the top. And all grain with young edges are coming from downstream. And this is very powerful to do vertical profile, because if you observe a slope break, like here I plot age versus elevation. If you do that here, you see that my cooling started when it was old and it was kind of slow cooling. But then I see a change in the break. I have a slope break, sorry. I have a slope break here. So this means we have an acceleration of exhumation at that moment. So vertical profile is very powerful to know when you have change in exhumation rates and so of denudation rate. And then we have to interpret if it is related to climate, tectonics, or both. Because as you can see on this figure, this is recent, it's not recent, but I mean, I think it's represent well all the different application of all the thermochronometers. And you can see you can apply this everywhere, in mountain range, in foreland, craton, or passive margin. There's a ton of application also in industry. That's very important for mining extraction to better understand hydrothermal activity, etc. It's very important for oil company because of the oil window is around 100 something, which is very close to fission tracks, apatite fission tracks closure temperature. Serpentinite exhumation, that could be useful for all the samples we collect, because we collect serpentinite here. So in my case, I use mostly for tectonic erosion and exhumation. And with Ari, we'll try to better work on heat flow and how this heat flow can affect rock, etc., and date at which moment this heat flow affects the rocks. And Alex, he worked on a lot of glacial erosion and river incision. So let's say more superficial processes. When they are sufficient enough, you can date. You can easily date thermochronology to date all of this. So I'm basically an expert of detrital thermochronology first. So I'm usually dating sandstone to try to get detrital information from here. You remember I showed you this blue line before. So when you have sediments can be buried and eaten again. So if your sediments are eaten, but not that much, you don't touch the helium. The helium stays inside, is not diffused. Same fission tracks are not annealed, still the same, it changed nothing. And so the information you have is the information from the source rock. So you have the thermochronology history of the source rock. If you eat a lot, we say that resetting the system. This is how we call it. When you reset your system, it means like, here I eat so much my sediments that I remove all the helium inside because I eat it too much. And all my fission tracks have time to anneal. So what I will record here as the last cooling event, which is often the exhumation of the basin. And if you have something in between, is also good information because often you will reset, for example, helium, but you will not reset fission tracks. So you know a thermal event of around 100 degrees happened. So it's also very interesting because if you know something of 100 degree happen, you can say, oh, we have a period of about 2 or 3 kilometers, same according to the geothermal gradients. So it's very useful to quantify how deep was the sedimentary basin too. And so about provenance, this is something we work a lot with Ari and try something. We will try to do something in the big Paleozoic basin we have close here from Ulaanbaatar. People they made provenance analysis on zircon, but they never did thermochronology there. So we will try to do that because so this is the kind of result we get. Usually we will have different cooling population because related to different sources. So source number 1, 2, and 3. And then if you collect sediment at different places of different ages, you can say, oh, for example, here I don't have source number 3, and here I don't have source number 2, because there was an orographic barrier, like a topography that avoids population free to arrive here, etc. So it's very useful to better understand paleogeography and make reconstruction of that. And the other point we do also with detrital thermochronology is what we call lag time. So in Paleozoic it's hard to do. Usually we do in a Neogene also. Mesozoic is a bit hard, but can works too. But you know, it's not because your topography is eroded that you cannot have information anymore. And the sediment, you preserve information. So here, it's very old rock that was eroded a long time ago. Here it's, and here red is rock a bit younger, but still not existing. It's rock you don't see anymore, but all these rock are here. So you just have to read the information and history in this rock, and you are able to reconstruct how was your landscaping, not landscape, how was your origin in the past, how if it was cooling fast, etc. So in this kind of case, what we do is we plot the time of closure temperature, so the time my sample was there, and when my sample arrived here, because the transport by erosion is very fast compared to the time of closure and then the time of period. So what we do is we plot in this kind of graph. And so if you have dots like that, like my sample here, they show quite a linear relation between my closure temperature age and my deposition age. When you have this kind of graph, it means that you have a steady state evolution of the origin. But if you have something like that, it means that your cooling is quite fast compared to the age of deposition. And so in this kind of case, what you observe is a growth stage. So in Andes, people work a lot on that, and it's quite clear which time is a growing stage and which time is a steady state. And when you have the opposite, you have orogenic decay. So this is very useful when you have data that work to better understand past orogenic history. As every method, we have limitations. So the first limitation in some rocks, you have no zircon, no apatite. So you cannot do anything. Because the lowest thermochronometers are with zircon and apatite. So sometimes you don't have enough uranium. Himalaya is okay, Mongolia for what I saw is okay, but if you work in Patagonia and Andes, there's very few uranium. So sometimes it's hard to get age. Also, I tell everything is a matter of cooling. So if the cooling or the exhumation is not strong enough, you will not record because the closure temperature is 110 for fission tracks and about 70 for helium. So if you have a cooling of only 40 degrees, for example, which is, let's say, 1 kilometer maximum, you will not record it by thermochron. Doesn't mean that nothing happened, just means that it's not sensitive enough to be recorded. So this is very important. When exhumation is too young, so most of the time it's not recorded again in the Andes. And when I started working in the Himalaya, I discovered that, yeah, when it's full of uranium, actually, you can record very, very young thermochron ages. So it's again a matter of uranium content into the grain. If exhumation is too slow, you spend too much time in the partial annealing zone or the partial retention zone. And so, as I told you before, you just remove all the helium and you just anneal all the fission tracks. So when you spend too much time in this area around 100 degrees, you reset everything and you will see nothing. And sometimes, so for detrital thermochronology, the main problem is not being able to detect population properly. Like if you have the source that cool at 30 million years and another one that cool at 40, you know, because we work by statistics, sometimes it's too close. And like the software will tell us, oh, we have one population at 35. So sometimes it's very hard to differentiate the sources when the exhumation age is too close. So I will just finish quickly with few examples in Patagonia that represent well the thermochronology, the use of thermochronology. So in Patagonia, you can see, as tell Alex before, so here you have the subduction zone, and more than 500 meters, 700 kilometers here, far, but I mean, in the ocean, they can still see deformation structure on seismic line. But on land, you can see that the Andean front is here, but we can see topography here, all this part. And so on my thesis, the main question was like, some people, they say, oh, main deformation of this front was Cretaceous, and others say, no, it's Miocene. So what we did, we collect rocks there, and we say, okay, if we have Cretaceous age, it should be main deformation during Cretaceous, and if it's Miocene age, main deformation during Miocene. And here's what we get. So previous data along the Andes, they only show very recent ages that shows that main exhumation event was during Miocene. But here, if you look at what we call the broken foreland, which is just an intraplate belt, you can see the intraplate belt is just made by Cretaceous or early Paleogene ages. If we want to model that, so it's all Paleozoic bedrock and Jurassic sandstone that I did here. So I first put a constraint here because I know during Paleozoic, so it was mostly Permian, Triassic, and also Jurassic. My rocks were close to the surface, so I have this constraint. Second constraint taken account by modeling are all the ages here that are Cretaceous, early Paleogene. Our last constraint is present day temperature. And then I asked the model to reproduce my data. And what I got is this. Except for a few samples, I will come back on it after. Most of the samples, they show a long-term exhumation or a fast exhumation, but everything during Cretaceous and early Paleogene. Nothing during Miocene. So we conclude that the main deformation of this belt was in Cretaceous. So some people were not so happy about, and they were looking at our data more in detail, and they say, look, in very few areas here and here, which correspond to this sample here, you have a fast cooling during Miocene. So it means you have fast exhumation during Miocene. So we were thinking, yeah, maybe it's true, and it's kind of very exciting because in that case, why it's locally we have strong exhumation or not? And then we look better at the data. This is a picture from Google Earth of the broken foreland. Here you have the Cretaceous deposits, and what is that, you think? What is these dark rocks all around my Cretaceous?
Cotton.
Basalt. All of this is just huge basalts everywhere. Everywhere in the foreland, we have huge basalts. So what we did is modeling again. And first thing I was like, oh, well, here we have a very fast cooling during Miocene. It's very interesting. So we were very happy to show that, yeah, in some area we have rapid Miocene. But then I saw all these basalts, and I was like, I should plot the age of this basalt on my graph. And there I plot the age. And the age of heating and cooling fits perfectly with the age of my basalts. And you see, I put no constraint in this area. The only constraint I put is the Cretaceous age of my sediments. So Argentina was not very happy about these results, but this just shows that all the recent cooling age we have in the foreland are related with the emplacement of basalts. And because, you know, we have a million years of volcanism, so we consider that we have a strong increase of geothermal gradient. And because of basalt, we have a small burial below basalt, so we just reset most of the things. We reset helium, but not fission tracks. So we know all the rocks were heated around 100 degrees in this area. And they were cooled very slowly because when the volcano stopped, the geothermal gradient returned to a normal temperature, and then you have cooling of the rock. So in this study, we just show that main deformation, which was about minimum 2 kilometers of, and it was a big unroofing, 2 kilometer unroofing of the foreland, occurred mostly during Cretaceous and early Paleogene. But as I told you, doesn't mean that there was no deformation in Miocene, but that this deformation was not significant as a Cretaceous one. And then last example, so just for provenance, because showing application is always easier than showing methods. So this is all the age we have in Patagonia, and you see that, again, most of the data along the Cordillera are very recent, and in the foreland, everything is very old. And the result we have with the title is like, in this area, we got all population, only in this area. And you see it's yellow stars. Here, also here. The yellow stars are Eocene sample. So for the Eocene rocks, what we got are all population, and for all the Oligomycene sediment we collect, we only have very recent population. So what does it mean? But during Eocene, the main source was there, which corresponds completely of the age of this rock we have around. So during Paleogene, we have post-erosion, because I told you we have strong deformation in Cretaceous, early Paleogene. And during Eocene, you just erode all these rocks. And so in the Eocene, you find all these deposits with all cooling age signature. But then what happened during the Oligomycene? So again, people were arguing, yeah, during Miocene, we have deformation, so we should see all grain 2 in Oligomycene, but I saw nothing. All my Oligomycene sediments show recent ages that are all derived from caldera, and we check also with zircon signature. And the zircon signature is quite clear that everything is derived from caldera, and so these intraplate beds here, north and south, were not eroded at all, or not significantly enough to be recorded in our sedimentary record. And so this just shows that main deformation was Cretaceous or Paleogene. And Miocene, you have deformation because the basalts I show you are tilted. That means you have a slight deformation, but the deformation was not that important. So thank you for your attention. I hope it was clear about the methods, and maybe you have ideas of what to do better with thermochron in Mongolia. But yeah, thank you.